Hello, everyone. Welcome to week 1, lecture 3. We're going to be talking about motion in one dimension. This is coming from chapter 2 of the textbook. We'll talk about position, displacement, velocity, and acceleration, then one-dimensional motion, and kinematics equations, and then a couple of examples at the end. So first up is the position vector. In the previous lecture, we talked about vectors and unit vectors in 2 dimensions. To introduce these topics, right now we're going to expand this to 3 dimensions. For now, we'll go back to 1 dimension after. So we have our 3D coordinate axes. X, Y, and Z. And then they're represented by the unit vectors I hat, J hat, and K hat. And then also on our 3D coordinate axis, we have the path of a particle here, and the particle itself, which is the dot. And we can see that there's a vector pointing from the origin to the position of the dot or the particle. So that here, and it's labeled R. It's also written in unit vector form up here, excuse me, where R equals X times I hat plus Y times J hat plus Z times K hat. And you can also see with this example that X, Y, and Z represent the values of the position along those axes. So that's what these dashed lines are, showing that along the x-axis, which is this one, X is the value of the X position there, X, Y, and Z for the rest. Next is the idea of the displacement vector. So instead of one position of the particle, we have 2 positions on the path given by T1 and T2, or time 1 and time 2. We also have position vectors for both of the particle, or for the particle in each position, so R1 and R2. And the displacement vector is the difference between the 2 position vectors. And it's given by the symbol delta R. Next, we want to talk about velocity, specifically average velocity first, which is the displacement divided by the time interval. And time interval here, so average velocity, displacement divided by the time interval, and then the time interval here is the time 2 minus time 1. And the time interval is a scalar, so it's only magnitude, not position. And so the velocity vector points in the same direction as the displacement vector, since time is not a vector. So that was average velocity, so like over a time period. But if we want to know the instantaneous velocity of the particle at a given moment, we need to reduce the size of the time interval so that the displacement vector approaches the actual path and becomes tangent to the path as the time interval approaches 0. So we see our separation between T1 and T2 is a lot smaller here. And the vector representing the displacement is, as far as we can tell, along the line of the path. So this also means that instead of change in position or displacement over change in time, we need the derivative of the position with respect to time. And this is the instantaneous velocity, or really what we will refer to as the velocity. A brief reminder about the derivative of a vector. The position vector R is given by X, Y, and Z magnitudes and the unit vectors here. So this is this part in the parentheses is the vector R. And when you take the derivative of a vector, you just distribute the derivative to each component, which gives you dx dt I hat plus dy dt j hat plus dz dt k hat. And this, in turn, or those in turn are the components of the velocity vector. So we have v sub x I hat, which is the derivative of x with respect to t. The same thing with the other two. And then units of velocity are in meters per second, because remember from the previous lecture, meters and seconds are those fundamental SI units that we use in physics. Acceleration, which is the change in velocity with time. Average acceleration, just like average velocity, is the change in velocity over the change in time. The change in velocity is the final velocity minus the initial velocity. But again, this is average, not instantaneous. For instantaneous acceleration, you have to reduce the time interval and take the derivative of the velocity with respect to time. So that's what we have here. And then each component of the vector is just the velocity in that component. So x in this one, velocity in the x direction, the derivative of the velocity in the x direction over time. And the units of this are meters per second squared. And that's just because we divided velocity by time another time. So that gives us 2 units of seconds in the denominator. Now, one-dimensional motion. So let's start with no motion, easy maybe. The position is given by this equation here, where x of t equals a, where a is just the position of the particle, and that's not changing. And we can look at the position graph, which is here, the position versus time graph. And we can see it's just a straight line. So the position is not changing with time. It remains at a, since the object is not moving. And the velocity graph here below, velocity versus time, the red line also shows the velocity during this time period, but it is at 0 because there's no motion. Now we have motion with constant velocity. The position equation is given as x of t equals a plus b times t. And we have a from before, which is the initial position of the particle. This time the particle's moving though. And then there's the b times the time term, which tells us how the position changes with time. So we get this in our position graph, we get this line with a constant positive slope. And the slope of that line is the velocity. So the slope of the line is b, and that is the constant velocity in our velocity graph. We also have accelerated motion. We have 2 examples here of accelerated motion. For the first one, the position equation is given as x of t equals a plus b times t plus c times t squared. And this is shown in this position graph A, where we see the slope changes over time. So initially it's just a slope of b, but then it increases over time because there's acceleration. Because remember, the slope of the position graph is velocity, and if there's acceleration, velocity is changing, so the slope of the position graph is changing. The other example is x of t equals d cosine omega t. And this gives us a cosine graph in B here, where the position oscillates as the slope changes. So the position oscillates between positive and negative d as the amplitude, and then the slope, with which you could see if you kind of put a tangential line along the path, you'll see that the slope is changing over time. Now we can look at an example of changes in motion, specifically of a car accelerating and braking, and also at rest. This time the acceleration plot is on the top, the velocity plot is in the middle, and the position plot is at the bottom. So let's start with position. The car starts at rest, so the position is 0 and doesn't change. And then it begins accelerating. So we see a positive slope, but it isn't constant. So it's a shallower slope here and a steeper slope here. And then we have a period of constant velocity where we have a constant slope in our position graph. And then we have the car braking, where it's kind of the opposite situation of the accelerating point, where the slope is steeper here and shallower here, showing us that the velocity is decreasing. And then finally, the car is at rest again. So it's at a different position, but that position doesn't change. So now let's compare those same time periods, rest, acceleration, constant velocity, braking, and rest again, with the other plots, or between the other plots. So the initial resting period for everyone is 0, velocity is 0, acceleration is 0. That makes sense. There's not motion happening. We looked at a graph already with no motion. Then in the acceleration period, we have, remember, the slope of this changing in the position graph, and we see in the velocity graph, we see a constant positive slope, which tells us that it is accelerating, because just like the velocity is the slope of the position graph, the acceleration is the slope of the velocity graph. So we see we have this constant positive slope here, and that is telling us that we have a constant acceleration, constant non-zero acceleration. And so that's what we're shown on the acceleration graph. Then we have our constant velocity time, which gives us this constant positive slope in the position graph, and that gives us a constant positive value of the velocity. And if the velocity is constant, that means there's no acceleration. So acceleration is back at the 0. Then we have our decreasing period or braking period. So again, our velocity goes from something bigger to something smaller. And we see that with this decreasing velocity on the velocity graph, and also with a constant negative slope. So our acceleration is then negative below the origin line here, so it's negative. And then finally, just our resting period, and everybody, acceleration and velocity are back to 0, but the position is at whatever position it made it to at that time. Okay. And then a brief look at graphs for a falling object. Starting at the bottom, we have a parabola. Again, this is the position is at the bottom, velocity is the middle, acceleration is the top. We're looking in the y direction this time. So the position is a parabola, showing that the object falls with increasing negative velocity, and we can see that in the velocity graph. It starts at 0, so that tells us that it starts at rest. And then the velocity graph has a constant negative slope. And we can compare what's happening between the two graphs, because velocity starting at 0 and the slope of the position graph is pretty flat, so that makes sense. And then it starts to get a steeper slope on the position graph, and we see that is more negative value of velocity. So it's still a larger velocity. It's just the direction that tells us, or that the negative sign tells us the direction. So that can be a tricky part when you're thinking about it, is remembering that the bigger negative number is still a bigger velocity. And we have constant negative acceleration the entire time. And this is the acceleration due to gravity. So 9.8 and negative 9.8 in this. Now I'm going to briefly derive some of the kinematics equations for constant acceleration, just to have handy. Okay. So we're going to start with velocity with constant acceleration. Velocity with constant acceleration. So we're going to just start with the acceleration equation, but so this equation, the average acceleration equation. Change in velocity over change in time. And then we're just going to expand this term out. So the final velocity minus the initial velocity divided by the time interval. And then we're going to do some algebra. Let's write it out first. Acceleration, the final velocity minus the initial velocity divided by the time interval. And then we're going to multiply both sides by the time interval and subtract both sides by the initial velocity. And this is going to result in velocity final equals velocity initial. Sorry, we're going to add it to both sides because it's it's negative. Velocity initial plus the acceleration times the time interval. So this is velocity with constant acceleration. Then we're going to look at position with constant acceleration. Oops. Position with constant acceleration. So I'm going to draw a beautiful graph really quick. So this is a velocity graph. We're going to say this is T final, this is T initial, this is V initial, and this is V final. Okay. Now let's break these up into some nice sections. So we have our triangle here and our rectangle. And so hopefully maybe you remember this from calculus, that the area under the curve here for velocity is the position. So if we can connect those both together. So first though, I'm going to give us some dimensions for finding the area under the curve. So the time interval is T final minus T initial. This height here is the initial x velocity, our initial velocity. It's fine. We're just doing one direction at a time. And then this is the change in velocity because it's final velocity minus initial. Okay, so then let's look at our two areas here. We have the rectangle. And so the area of the rectangle is just the two sides multiplied by each other. And so one side is the displacement and the other is the initial velocity. So initial velocity times the displacement. And then the triangle is 1/2 base times height. So 1/2 the displacement times the time interval. And we also know that that the displacement in x is equal to the acceleration times the time interval. So we can plug that in instead. So we have 1/2 the acceleration times the time interval squared. So now the total area under the curve is those two added together. And that's also the displacement. So the displacement change in x is the area of the rectangle plus the area of the triangle. So the initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. And we can also expand out the displacement term to x final minus x initial and add x initial to both sides. So this could give us an equation specifically for the final position. So x final equals x initial plus the initial delta t plus 1/2 a delta t squared. And this is referred to as, or I will call it at least, the long kinematics equation. So just so you know which one it is. 1 second, run out of space. Last one is velocity and displacement with constant acceleration. These are all with constant acceleration, if you didn't notice. And zero acceleration also counts as constant acceleration. Okay, so now we're going to start with the acceleration equation. This is the average acceleration equation. And we can rearrange it to solve for time. And we can have the final velocity minus the initial over the acceleration. And then we have our displacement equation from above, or I guess on the previous page. So we can use that. And I'm not going to show all of the algebra for this because I don't necessarily expect you to be able to recreate this or anything. I just want to show you where these equations come from before you have to use them a bunch. So now we can just plug in delta t into both equations. And like I said, I'm not going to show all the algebra, but if you wanted to do it, feel free. So, but it gives us the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. Okay, back to the slides real quick. Okay, and so the slide also has those equations. And these can be in any direction, X, Y, or Z, but we just can't mix the terms. For example, you can't use the Y acceleration when finding the X velocity. And that's kind of a common thing that people can get mixed up. Because for free fall or projectile motion, which we'll get to, not today, but we will get to it. But in those situations, there isn't necessarily acceleration in the X direction, but there is acceleration in the Y direction. But if you're if the problem requests X position or X velocity, people can sometimes accidentally bring the Y acceleration into it. So you got to be careful. So just to review them, the final velocity equals the initial velocity plus the acceleration times the time interval. Then we have the final position. This is the long kinematics equation. The final position equals the initial position plus the initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. And finally, the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. So now I have 2 examples for you where we will use those equations. Okay, so this is sample problem 2-9 in the textbook. So the problem is you drive your car at 15 meters per second, you hit the brakes and stop in 1.5 seconds. How far do you travel as you stop? So important strategy we use in solving these kind of physics problems is we write down what we know, so our knowns, based on the problem itself. So let's see. We know our initial velocity is 15 meters per second because they gave us that. We know the time interval is 1.5 seconds. And then one thing that isn't explicitly said but is implied is that the final velocity is 0 because we're coming to a stop. And we can also define our initial position as 0, just because we have the freedom to be able to do that. And it's good just in case we need it. So then we should write our unknowns. So we don't know the final position, and we don't know the acceleration. And what we want is the final position. So let's take a look at those kinematics equations. I'm going to drop the subscripts for now, just because it takes up, or the x subscript. We're just going to be working in the x direction right now. So v final equals v initial plus the acceleration times the time interval. And then we have x final equals x initial plus the initial velocity times the time interval plus 1/2 acceleration times the time interval squared. And finally, the final velocity squared equals the initial velocity squared plus 2 acceleration times the displacement. Okay, so now what I do, and I recommend this especially when you're getting comfortable with kinematics equations, is look at it and see what we know and what we don't know. Okay, we know the final velocity, we know the initial velocity, we don't know the acceleration, but we do know the time interval. Okay, we might use that problem because there's only, or that equation, there's only one thing we don't know. Okay, for this one, we don't know the final position, we know the initial velocity and the time interval, don't know the acceleration, and like I said, we know the time interval. So there's 2 unknowns in that equation. Then this one, we know this, and we don't know either of those. So this tells me there's only one equation with only one unknown. So we should probably start there and solve for acceleration. And then we'll be able to plug in to either of these other equations once we know acceleration. So let's do that first. Find our acceleration. V final is V initial plus acceleration times the time interval. And we can just do some algebra where we subtract V initial from both sides and divide both sides by the time interval to get us acceleration by itself. So this will be V final minus V initial over the time interval equals the acceleration. And V final is 0 because we're coming to a stop. So this is negative 15 meters per second divided by 1.5 seconds. Yeah. So that gives us negative 10 meters per second squared, because remember, acceleration is meters per second squared. Okay, cool. Then we can just pick whichever equation we want to use. I think I'm going to use the long kinematics equation because then I don't even have to do any like rearranging because we want to know the final position. So that's convenient. But you could use the other one if you wanted. Okay, let's do it. X final equals X initial plus V initial delta T plus 1/2 A delta T squared. Now we can just plug in our numbers. Well, I guess actually first we can say that that is 0. And then we have 15 meters per second times 1.5 seconds plus 1/2 negative 10 meters per second squared times 1.5 seconds squared. And this gives us a final position of 11.25 meters. So that's how long you travel once you put on the brakes. That's how far you travel in that 1.5 seconds. So I'm gonna really quickly just go back through what we did. Obviously you could rewind to do that yourself, but that's what I like to do. So we wrote down our knowns, the initial velocity, the time interval, the final velocity, which was implied because we're coming to a stop, and then we got to decide the initial position. It's easier just to make it 0. And then the unknowns were the final position, which is what they asked for, and the acceleration. Then we looked at the kinematics equations and looked for what we know and what we don't know. There was only one equation with one unknown. So that's where we started, even though it wasn't the thing we were asked for, it was the acceleration. But we found the acceleration and then we plugged that into a different equation because what we were asked for was the final position. Next up, we are going to do chapter 2, exercise 57. So a ball is thrown straight up, takes 2.25 seconds to reach a height of 36.8 meters. What was the initial speed? What was the speed at this height? Or what is the speed at this height? And how much higher will the ball go? So start with what we know and what we don't know. Start with knowns. Let's see. So our time interval that they give us is 2.25 seconds. And the height they give us, which we'll just call it Y1 for now, 36.8 meters. And then what else do we know? Well, we know, we can say that Y initial was 0 because it came from the ground. I don't know if we'll need that. We'll see. It's good to keep track though. And then the other thing is this is free fall. So that means the acceleration is the acceleration due to gravity, which is negative g, which is acceleration due to gravity, or negative 9.8 meters per second squared. Okay, and we should write our unknowns. So we don't know what the initial velocity is, or actually I'll write that V naught, so we're keeping our subscripts the same. V naught, we also don't know what V1 is. That's one of the things we're asked for. And then we don't know what Y final is. It's another thing we're asked for. Yeah, I think that's all. Then we can look at our kinematics equations again. So let's write those down. We have V final equals V initial plus second, acceleration times the time interval. Then we have the long kinematics equation. And since this is in the Y direction, I'm just going to switch from X to Y. So Y final equals Y initial plus the initial velocity times the time interval plus 1/2 acceleration times the time interval squared. And then V final squared equals V initial squared plus 2A delta Y, or the displacement. Okay, cool. Let's do our going through and seeing what we know. Okay, we don't know that. We don't know that. We know this and we know that. Not super helpful. Let's see. We know this and this. And sorry, we are starting with finding the initial velocity. So our initial and final are slightly different depending on which part of the problem we're doing. But we'll look at that in just 1 second. We don't know. Oh, I'm sorry. We do know what these are in this one. Wrong symbol. We know Y final. We know Y initial for that. We don't know that, but we want it. We know that and that and that. Okay, it looks like we might be using the long kinematics equation to find the initial velocity. And we don't know the final velocity, don't know the initial velocity. We know the acceleration and displacement, but again, that's not helpful if we have two things we don't know. So we're going to use the long kinematics equation, but before I get into it, I should draw the situation a little bit so that we are able to think about the different kind of parts of the situation. So we have our ball thrown up from the ground. So this is y naught equals 0, and v naught is we don't know. Okay, and then we have the position here of y equals 36.8 meters. Yeah, 36.8 meters. We don't know, and I'm going to call this y1 and v1. We don't know what the velocity is. And we know the time interval to get here is, I forgot, 2.25 seconds. And then there's some other point where we have y final, and we don't know what that is. We know that that velocity will be 0 because that is what happens with this sort of motion is we give it an initial velocity, it goes up as high as it can until its velocity is 0, and then it comes back down. And we don't know how long it takes to get there either. Okay, and this whole time, acceleration is negative g. Okay, so when we were looking at our kinematics equation, we were going for this sort of interval here from the ground to the height we were given. So now let's go back to the long kinematics equation. Let's see. Y final equals y initial plus v initial delta t plus 1/2 a delta t squared. Okay, and let's just write what our variables are, or like our numbers are, so that it's easier to plug it in. So y final is that 36.8 meters. Y initial is 0. V initial, and I'll just write these as not again, so we're consistent. We don't know. Time interval is 2.25 seconds, and acceleration is negative g, or negative 9.8. Okay, so now we can plug things into that equation. So let's see, y final, oh wait, before that, we should probably solve for the thing we want. It's a little easier to do it variable wise. So y final equals y initial plus v initial delta t plus 1/2 a delta t squared. So we want to get v initial by itself. So we'll subtract y initial from both sides. We'll subtract 1/2 a delta t squared from both sides. And then we'll divide everything by delta t. That will get us v initial by itself. So let's see, y final minus y initial minus 1/2 a delta t squared, whole thing divided by delta t, equals the initial velocity. And then we can plug in our numbers. Might give myself a little bit more space for that. There we go. Okay. Y initial is 0, so we don't have to worry about it. So we have 36.8 meters minus 1/2 negative 9.8 meters per second squared times 2.25 seconds squared, all divided by 2.25 seconds. So this gives us an initial velocity of, there we go, 27.4 meters per second. Okay, so that answered part A. Now let's go back up really quick. Part B says, what is the speed at the height given? So we want to know what V1 is next. So let's go to the next page and do our kinematics equations again. Okay. V final equals V initial plus A delta T y final equals y initial plus v initial delta t plus 1/2 a delta t squared, and v final squared equals v initial squared plus 2a delta y, or displacement. Okay, really quickly, we'll go through. We don't know this, we know that, and the acceleration and the time interval, so we could use that equation. We know these. Oh, this doesn't even have the final velocity, so we don't want to use that equation. And then this and these. Okay, so I think I'm just going to use this first one because I don't have to deal with a square root, and it's already solved for us, so we can just plug in our numbers. V final equals V initial plus A delta T, and V initial we just found is 27.4. So we'll just plug that in. 27.4 meters per second plus negative 9.8 meters per second squared times 2.25 seconds. And this is 5.33 meters per second. So that is velocity 2 is actually what, or actually I'm calling that velocity 1. I'm sorry, I'm confusing you with my labeling. That is velocity at y equals 36, yeah, 36.8 meters. Okay, cool. Last part asks for how much higher the ball will go after this. So that's asking us for a y final, but let's think about this really quick. I'm just gonna, actually, I'll just go back to the drawing. Here we are. So we did this interval. We want this interval now. And we actually, what we want is y final. And we don't know the time interval there. But we know the initial and final velocities, and we know the initial position. So let's take a look. I'm not going to rewrite the kinematics equations, but let's just take a look. So this one does, here, let's do a different color actually. This one does not have the final position in it. This one does, but it also has time, and we don't know that time interval. And this one, it looks like, so we know the final velocity is 0. We know the initial is this right here, this 5.33. We know the acceleration, and then displacement is y final and y initial. We know y initial. Oops, I don't know why I crossed it out. I meant to put a check mark. We don't know y final, but that's what we want. Okay, so we're going to use this equation. Let's bring it down here. V final squared equals V initial squared plus 2a delta y. Actually, sorry, I'm going to write that as y final minus y initial. Because what we actually, oh, see, I'm messing myself up. We actually want the displacement. So actually we don't need, because it asks how much higher, not how high total. It's a little tricky. Okay, let's do some algebra. Minus v initial squared from both sides, and then we're going to divide 2a from both sides. And that gives us v final squared minus v initial squared divided by 2 times the acceleration is the displacement. And the final velocity is 0 because it's at its highest point. This is 5.33 meters per second squared divided by 2 times negative 9.8 meters per second squared. And this is, I'll just plug it in my calculator real fast because I did it the other way before where I solved for y final, which is not what they asked for. Okay, yeah, 1.5 meters delta y. So that's how much higher it's going to go. And that makes sense because, so we looked and our initial velocity was 27.4 meters per second. And then when it got to 36.8 meters, the velocity was 5.33. So it's really decreased, which makes sense because the acceleration was acceleration due to gravity, which was pointing down. So it was counteracting the velocity. So it makes sense that it wouldn't go up that much higher. Okay, really quickly, we will go over the problem. So we wrote down our knowns. We had the time interval. We had this initial height, or height 1. We were able to establish that it starts from the ground, so we can call that 0 for the initial position. And then this was free fall, so the acceleration is acceleration due to gravity pointing down. Our unknowns were the initial velocity, the velocity at 36.8 meters, and then wasn't actually the final position, but the that final chunk of displacement. So we were going to find the initial velocity first, since that was what they asked for. So we looked at our kinematics equations, and we saw that only the long kinematics equation had just one variable. We didn't know everything else had 2, so we couldn't use those. So then I also drew the situation for us, which really I should have done before the kinematics equations. That was my bad. So just to go over that again, we start out on the ground with a y position of 0, and we don't know what the velocity is. Then we get to this 36.8 meters in 2.25 seconds, and we don't know what the velocity is at that position either. Then we get to this final height, and we know the velocity there is going to be 0, because that's what defines the final height. We don't know what that time interval is. And then this whole time, we know the acceleration is negative g, or negative acceleration due to gravity, 9.8. So now back to the long kinematics equation. I also wrote out our variables to remind us, and then we needed to solve for the initial velocity, and we got 27.4 meters per second. Then we needed to solve for the velocity at 36.8 meters. So we looked back at the kinematics equations, and for that one, the initial velocity we know now. So looking at the wrong colors, look at the blue for this part. We used this first equation because we only didn't know the final velocity, and we didn't have to do any algebra to solve it. So that gave us 5.33 meters per second. And then finally, we wanted to know how much higher it goes from that 36.8 meters. And this is the purple now. We didn't want to use the first equation because it doesn't have the position in it. And then the next two have the position, but we didn't have the time. And then the last one only had one thing we didn't know, which was that final position. We kept it as displacement because, again, that's what they're asking for by saying how much higher does it go. It's asking for the displacement, not the final y position. We solved for that, and we saw that it travels 1.5 more meters before velocity is 0, and then it reaches its turnaround point. Okay, 2 examples. Hopefully those were helpful. I think I have one last slide for you. Maybe. I don't think it wants to show you. Okay, there we go. Now, just a reminder of what is next. This was your last lecture of the week. Yay. Now you should complete your post-lecture assignments, the self-check, discussion post, and application assignment. And you now also have all the information you should need to work on the practice assignment for this week. So, good job.